Somewhere out past the orbit of Neptune, a photograph is still traveling toward Earth that was taken more than 3 decades ago, and the spacecraft that took it had already said its goodbyes to every planet it would ever see up close. 6 minutes. That is roughly how long it would take a radio signal from the moon to reach us, and it sounds almost nothing compared to what Voyager 2 actually deals with every single day, where a single message now takes the better part of 20 hours, just across the distance between here and there. But 6 minutes is also, strangely enough, close to how long it took for one particular command to be carried out in August of 1989. A command that told Voyager 2 to do something it had never been asked to do before. Turn around, point its cameras backward away from the sun, and take one last look at the world it had just flown past forever. What came back in that image, and what the spacecraft has kept discovering ever since, turned out to be far stranger than anyone in that control room expected. And it did not need a single exaggeration to shock the people watching it happen. Here is the full story of what Voyager 2 saw when it turned back, and what it is still finding out there today. To understand why that moment mattered so much, you have to go back to where the mission actually started. Voyager 2 launched on August 20th, 1977, technically weeks before its twin Voyager 1, even though Voyager 1 ended up taking a shorter, faster path, and arrived at several destinations first. Voyager 2 was given the longer road on purpose, a trajectory built around a planetary alignment so rare it only lines up once every 175 years, letting a single spacecraft use the gravity of one giant planet to fling itself toward the next, saving enormous amounts of fuel it never could have carried otherwise. That decision is the only reason Voyager 2 remains the only spacecraft in history to fly past all 4 of the solar system's giant planets in a single mission: Jupiter, Saturn, Uranus, and Neptune, each visit adding to a list of discoveries that reshaped what scientists thought they understood about the outer solar system. At Jupiter, instruments spotted volcanic activity on the moon Io. At Saturn, its rings turned out to be built from thousands of narrow ringlets rather than a few broad bands. At Uranus, cameras revealed a planet tipped almost completely on its side, its magnetic field oddly offset from its physical spin axis in a way nobody had modeled in advance. Each flyby was treated internally as the final act. Nobody was certain the hardware, built with technology that predates the pocket calculator and raw processing power, would survive long enough to reach whatever came next. Then came Neptune in August of 1989, the last planet on Voyager 2's itinerary, and the final chance to see an entire class of world up close before the spacecraft pushed on into the emptiness beyond. The flyby itself delivered exactly the kind of discoveries the mission had become known for: a storm system nicknamed the Great Dark Spot, roughly the size of Earth. Ice churning in Neptune's atmosphere. The fastest winds ever measured on any planet in the solar system, moving at speeds that would flatten anything built by human hands. Geysers of nitrogen erupting from the icy surface of the moon Triton, spraying dark material for miles across a world so cold it barely registers on any scale built with human comfort in mind. All of that had already been captured as Voyager 2 approached and passed through the Neptune system, cameras facing forward, doing exactly what they had been designed to do at every previous stop. But then mission planners at NASA's Jet Propulsion Laboratory made an unusual request. Instead of simply letting Voyager 2 continue outward and shutting the cameras down for good, they asked engineers to turn the spacecraft around one final time and look back at what it had just left behind. That single decision produced one of the most quietly haunting images in the entire history of planetary exploration. A thin crescent of Neptune lit from behind by a sun now more than 2.7 billion miles away, its blue disk reduced to a sliver against total darkness. Beside it, an equally thin crescent of Triton, caught in the same farewell frame, the two worlds sharing one photograph for what would be the only time any spacecraft would ever capture them together from that particular angle. It was never a scientifically necessary image in the way the earlier data had been. There was no new discovery hiding inside those two crescents that couldn't already be inferred from prior instrument readings. And yet almost everyone who worked on the mission has described that photograph as one of the most emotionally significant moments of the entire project, because it was the closest thing Voyager 2 would ever have to a goodbye. After that frame was captured, the cameras were switched off. They have never been turned on again, and given the spacecraft's rapidly shrinking power supply, they almost certainly never will be. What makes that farewell frame worth returning to now, decades later, is not simply nostalgia. It is that turning Voyager 2 around, even briefly, even just once, revealed something people tend to forget about: a mission built entirely around moving forward. Sometimes, the most important discoveries come not from what a spacecraft sees ahead of it, but from what it notices when it looks back at where it has already been. And in a strange way, that is exactly what Voyager 2 has continued doing ever since, just not with cameras anymore. Its remaining instruments, the ones still drawing power nearly 50 years after launch, spend their time looking backward in a different sense, sampling the plasma and magnetic fields immediately behind the spacecraft as it plows through interstellar space, effectively studying the wake it leaves as it moves, the same way you might glance over your shoulder at the trail you've cut through deep snow. Both Voyagers carry something else that only makes sense as a message meant to be looked back on, quite literally, by whoever or whatever might eventually find it. A gold-plated record bolted to each spacecraft's side, containing sounds, images, greetings, and dozens of languages, and a carefully chosen selection of music meant to represent something true about life on Earth, without claiming to speak for all of it. The team behind that record, led by astronomer Carl Sagan, spent months arguing over exactly what belonged on it, aware that whatever they chose would likely outlast every institution, every language, and quite possibly every trace of the civilization that built it. That record is still out there right now, sealed behind Voyager 2's antenna, moving away from home at roughly 10 miles every single second, carrying humanity's one attempt at a backward glance toward Earth for an audience that may not exist for millions of years if it exists at all, because there is essentially nothing in interstellar space to slow it down, damage it, or wear it away the way weather and erosion would on Earth. Scientists have estimated that the record itself, engineered specifically to survive the harsh conditions beyond the solar system, could plausibly remain readable for hundreds of millions of years, long after the sun itself will have changed, and long after anything resembling human civilization, as it exists today, could possibly still be around to remember having sent it in the first place. Even long after Voyager 2 stops transmitting anything at all, even long after every last instrument goes permanently dark, that record keeps moving, keeps existing, and keeps carrying its message outward regardless of whether anyone is ever left to send a reply. By the late 1980s, once the planetary tour had officially wrapped up, both spacecraft kept going, eventually reaching the heliopause, the boundary where the sun's influence finally gives way to true interstellar space. Voyager 1 crossed that line first in 2012. Voyager 2 followed in 2018, becoming only the second human-made object ever to leave the vast bubble our sun carves out of the surrounding galaxy. And that crossing is where the story of Voyager 2 turning its attention backward becomes something closer to an ongoing discovery than a single dramatic moment. Researchers had assumed for decades that the transition out of the heliosphere would be gradual, plasma density and magnetic field strength shifting slowly across some wide, blurry boundary. Instead, both spacecraft detected something closer to a sharp edge, plasma density jumping abruptly the moment each one crossed over, more like passing through a real wall than drifting through a fade. Voyager 2 had a working plasma instrument at the exact moment of its crossing, something Voyager 1 did not have available 6 years earlier, giving scientists their most detailed direct look yet at what that boundary genuinely looks like, rather than having to reconstruct it indirectly after the fact. What Voyager 2 found once it was fully inside interstellar space is where things get genuinely strange, and where the phrase shocked the world starts to earn its place without needing a single invented detail. Scientists had built models predicting what the plasma and magnetic fields beyond the heliosphere should look like, based entirely on theory and indirect solar wind measurements taken from much closer to home. Voyager 2's readings did not match those predictions. Magnetic field measurements from just beyond the boundary showed patterns that theoretical models had not anticipated, hinting that the local interstellar medium, the thin cloud of gas and dust the sun is currently drifting through, is considerably more complicated and less uniform than anyone had assumed before an actual spacecraft was sitting inside it to check. There was no exotic explanation required. It simply reflected the plain reality that nobody had ever collected direct measurements from that exact region of space before, and reality, once again, turned out to be messier than any model built from a comfortable distance back on Earth. Then, in the summer of 2023, Voyager 2 gave engineers a scare that came closer than almost anything before it to ending the mission entirely. On July 21st, a routine sequence of commands sent from Mission Control accidentally caused the spacecraft's high-gain antenna to tilt about 2 degrees off target. 2 degrees sounds trivial, the kind of error nobody would notice pointing a flashlight across a room. But at more than 12 billion miles away, a 2-degree misalignment was enough to sever the connection completely. Voyager 2 stopped receiving commands from Earth, and its signal became too faint and too poorly aimed for the deep space network to make sense of. The spacecraft's built-in safety routine, designed to automatically reset its orientation several times a year, was not scheduled to run again until mid-October, nearly 3 months away, and nobody at NASA could say for certain the aging power systems would survive that long without any way to intervene. Engineers at the Deep Space Network's giant dish in Canberra, Australia, attempted something that had essentially never been tried at that distance before, an informally nicknamed Interstellar Shout, maxing out the most powerful transmitter available in NASA's network in the hope it would be strong enough to reach Voyager 2's antenna even while it sat pointed slightly away from Earth. The command took over 18 hours just to arrive. Then came another wait of similar length for any response to make the trip back. On August 4th, 2023, the signal returned. Voyager 2 had received the shout, repointed itself, and resumed normal operation as if nothing unusual had happened at all, closing out the longest gap in communication the mission had experienced in its entire history up to that point. That close call exposed something people tend to underestimate about a spacecraft this old. Both Voyagers run on radioisotope thermoelectric generators, devices that convert the heat from the natural radioactive decay of plutonium-238 into electricity, a process that cannot be paused, reversed, or refueled. Each spacecraft loses roughly 4 watts of available power every single year. With no solar panels capable of helping this far from the sun, and no possibility of ever sending a repair mission this deep into interstellar space. The only real tool NASA's engineers have left is deciding which systems to switch off, and in what order, to stretch the shrinking supply as far as it will possibly go. Each Voyager originally carried 10 separate science instruments. Most have already been shut down over the decades, largely because they were built to study planets up close and had nothing left to observe once the spacecraft moved into open interstellar space. In October of 2024, NASA switched off Voyager 2's plasma science experiment. In March of 2025, its low-energy charged particle instrument went dark as well, a shutdown command that took roughly 23 hours just to physically reach the spacecraft, a small but vivid reminder of exactly how far away this machine actually sits. According to NASA's own mission updates, its cosmic ray subsystem is scheduled to be switched off sometime in 2026, leaving the spacecraft down to just its magnetic field and plasma wave instruments for the foreseeable future. And yet, even with instruments disappearing one by one, Voyager 2 keeps looking backward at the space directly around it. It keeps finding things nobody expected. Its magnetic field readings continue to hint at structure in the interstellar medium that earlier models never predicted. Its plasma wave instrument, one of the last still running, continues to pick up faint density fluctuations that researchers are still working through, data that exists nowhere else in the world because no other human-made object has ever traveled far enough to collect it. If everything continues roughly according to current projections, NASA expects both Voyager spacecraft to keep at least one working science instrument running into the early 2030s, more than half a century after launch, before power finally drops too low to keep anything meaningful operating at all. Even after every instrument eventually goes silent, engineers expect the spacecraft could technically continue transmitting basic engineering telemetry for a little while longer. A faint signal confirming the machine is still there, right up until the power finally drops below the threshold needed to run anything at all. None of that scientific value would exist today without the people who spent decades keeping this mission alive long enough to reach it. Ed Stone, who served as the Voyager program's chief scientist from before launch all the way through both heliopause crossings, oversaw the project through every major flyby, Jupiter, Saturn, Uranus, and Neptune, before eventually stepping back from that role after devoting more than half his life to a single spacecraft. That length of institutional memory is genuinely difficult to replace, on a mission where the original engineers who built the hardware retired long ago, and where some of the original schematics exist only on paper in physical archives, rather than in any searchable digital format. Every current member of the Voyager team inherited a machine they did not design, running software written in a language most modern engineers rarely touch, and every one of them is now responsible for decisions that will remain permanent the moment they are made. There is no version of this mission where a mistake gets quietly corrected later. 12 billion miles away, corrected later simply is not an option. It is also worth remembering that Voyager 2 was never alone in turning backward to look at what it left behind. Its twin, Voyager 1, did something similar in February of 1990 after completing its own planetary tour years earlier, when it turned its cameras around one final time at the request of Carl Sagan himself and captured the solar system from roughly 4 billion miles away, a photograph in which Earth appears as a single pale blue pixel suspended in a sunbeam, smaller than a grain of dust against the surrounding darkness. That image became one of the most quoted pieces of writing and photography in the history of space exploration, not because of anything scientifically remarkable inside the frame, but because of what it forced people to confront about scale, distance, and how small the entire human story actually looks from far enough away. Voyager 2 never captured its own version of that particular photograph. Its final farewell was reserved for Neptune and Triton rather than Earth. But the instinct behind both moments was the same. Before pushing on into a darkness with no return trip, someone in mission control wanted one last look back at what was being left behind, understanding that the chance would never come again. There is something worth sitting with in all of this, without needing to add a single invented detail to make it feel significant. This is a machine built with 1970s technology, using computers with a small fraction of the processing power of a modern calculator, running on a power source that has been quietly fading since before most of the people currently operating it were even born. It turned its cameras backward exactly once over 3 decades ago to capture a farewell photograph of a planet it would never see again, and then spent the following 30 plus years continuing to look backward in every sense that still mattered, sampling the space behind it, holding onto humanity's one message to the wider universe, and occasionally reminding everyone on Earth just how thin the margin for error has become on a spacecraft this far from home. Suzanne Dodd, the current Voyager project manager at NASA's Jet Propulsion Laboratory, has spoken candidly in public updates about how deliberately the team now rations what remains, treating each instrument shutdown as the price of keeping the spacecraft alive as long as possible, rather than accepting an earlier, more abrupt end to the mission. Every decision about which system to switch off next carries real weight, because once an instrument goes dark, there is no scenario in which it ever comes back on again. What makes this story worth telling in 2026 is that we are very likely watching the final stretch of an achievement that will probably never be repeated in quite the same way. Future spacecraft will eventually travel farther, carry sharper instruments, and send back more detailed data, but they will not be Voyager 2. They will not carry the specific golden record assembled by a team led by Carl Sagan in the 1970s. They will not have flown past all 4 giant planets on a trajectory that depended on an alignment unlikely to repeat for well over a century. And they will not have turned around just once to take one last look at a world already fading behind them, only to keep discovering new things about the emptiness ahead ever since. NASA's own engineers have said, in plain terms, that every additional day either Voyager manages to keep operating is essentially a bonus nobody fully expected to get, and that any given transmission could, in principle, turn out to be one of the last useful signals the mission ever sends. That is not a manufactured mystery designed to make the story feel bigger than it is. It is simply the honest, ongoing reality of trying to keep a 50-year-old machine functioning at the very edge of what our species has ever managed to reach, using hardware nobody currently working on the project actually built, powered by a source of energy that has been fading since before most of them were born. Somewhere out past the edge of the solar system right now, moving through interstellar space at roughly 10 miles every second, completely alone, running on a power supply with a hard and permanent expiration date, Voyager 2 is still listening for our commands, still sending its readings home, and still, in its own quiet way, looking backward at everything it has left in its wake. It turned around once, over 3 decades ago, for one long final look at a world it would never see again. And in doing so, it left behind an image that still moves people who were not even alive when it was taken. It has been turning around in a smaller sense ever since, sampling the space behind it, carrying humanity's one message outward regardless of whether anyone out there is left to receive it. However many years it has left, that alone remains one of the most quietly extraordinary things humanity has ever built.